Hello friends, you are welcome to the fourth episode of my series Embedded Design in Electrical Power Domain. We have seen how to get RMS value, how to calculate active power, that is VI cos phi, and today we will see how to calculate harmonic components of a waveform. Now harmonic components arise in any repetitive waveform when it is not a pure sinusoid. If it is a pure sinusoid, it will have only one component, that is a fundamental component or the first harmonic. But if it is not a pure sine wave, but it is repetitive at a fixed repetition rate, then it will have a large number of harmonics, a large number. So we are going to see what it is all about. So here we say that to extract nth harmonic, what do you do? This is the equation we will use to extract the nth harmonic. Here Fn is nth harmonic and it is made up of what? Fk into e to the power j pi nk by 2. This is the standard formula. We add them up and that is where we land in the value of Fn. I read it out, where Fn is the component of nth harmonic and Fk is the kth sample of waveform. So we are taking n number of samples, capital N number of samples, and we are going to perform this and then do their sigma. That is what it is all about. Here n is the nth harmonic, k stands for kth sample of the waveform, and capital N is the total number of samples you take per cycle. So to evaluate fundamental component, that is the first harmonic, we take n is equal to 1. For second harmonic, we take n is equal to 2 and so on. So the equation becomes, if n is equal to 1, it becomes F1 is equal to 1 to capital N Fk e to the power j pi into 1. See here, I have written 1 here. This one is because of this one, n is equal to 1, because I am trying to extract the fundamental component or the first harmonic. But here you have to remember one thing, we must ensure that Nyquist criterion is not violated. This is very crucial and very critical. For example, if the basic frequency is 50 Hertz, let us say, and we want to extract 10th harmonic, then Fmax is equal to 50 into 10, which is 500. You remember Fs and Fmax, that is we started with while trying to calculate the RMS value, right? So Fs is important. Fs is the sampling frequency. Fmax is the highest component of interest, highest frequency component of interest. Then Fs has to be greater than or equal to 2 times Fmax, or Fs is greater than 1000 samples per second, correct? So if we take 20 samples per cycle, then for 50 Hertz signal, the sampling rate will be 20 into 50, which is 1000. You get that? We are taking 20 samples in one cycle, and there are 50 such cycles in 1 second. So total number of samples you take is 1000. Is the speed of sampling. Actually, we take only 20 per cycle, 20 samples per cycle. So we are going to use this equation next. Again, so we see that F1 is this. We have just now seen why it is 1 here and why this is 1 here. So F1 is equal to 1 to n Fk. Now this e to the power x, e to the power jx is written as cos x minus j sin x. This you remember from your basic mathematics course. So e to the power j theta is equal to cos theta minus j theta. Here theta is pi into 1 into k by 2, or simply pi k by 2. So it is pi k by 2 cos pi k by 2 minus j sin pi k by 2. Since we are taking 20 samples per cycle, The angle between consecutive samples is 360 upon 20 degrees. One cycle means 360 degrees. And so we want to find out after how many angles, what angle I'm taking sample in terms of angles or degrees. So I say 360 degrees mein, in 360 degrees you are taking 20 samples. So your samples are separated by 18 degrees. Note that the coefficients, namely cos pi k by 2 and minus j sin pi k by 2, play a crucial role. So the next step is to generate this set of coefficients. So cos 0 pi upon 180, 18 pi cos 118 pi upon 180, cos 36 pi upon 180, and so on, up to cos 360 pi upon 180. Similarly, the sine components. So we had done this cos components like this, and the sine components will appear like this. So this is the whole thing that you are going to do. The whole thing. You try to understand this. For that, let us take a look at this. What you should really do is store these values. Which values? The coefficients. Tables, one for cosine coefficients and the other for sine coefficients. When you start implementing, this is how you proceed. After this, we are in a position to realize equation 1 and extract fundamental component. With the same logic, we can evaluate higher harmonics. To verify and understand better, you should implement it first in an Excel sheet, as shown next. Okay? So if you do it in the Excel sheet, you will fully understand the entire process. And then when you start coding or even designing hardware, you will not make mistakes. This picture completely represents the entire process of practical extraction of harmonic components. Practical. So there is a hardware part of it and there is a software part of it. Everything is covered in this. So pay close attention. First thing first, we have a voltage vector V1. It is a square wave. In our case, we have taken a square wave. So we have a square wave here, V1. Then we cannot apply any value we want to the ADC. There is a limit, upper limit of the value, and also the limit of to ensure that you always apply positive, right? So first you attenuate it to acceptable value. We should know what is the highest value of V1 you will get, and at that time this should remain within control, that is within the limitations of the AD converter. So this is going in positive as well as negative direction. So it is this, look at this red one. 1 volt positive, 1 volt negative. It is going like this. This is a basic thing. Starting from here, goes up, goes here, 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 and so on. Now we cannot say that I will start measuring only when it is 0 and starts increasing. We cannot say that. We start measurement at any time. So we have started measurement at this time. So this is the 0 instant here, and this is the 0 voltage here. So first thing we do is we shift it up by 1.5 volts, assuming that R2 never falls below minus 1.5. So in the worst case, it can be minus 1.5. To that we have added plus 1.5, and here it will be 0. In general, this will be above 0 all the time. So that is Vs. Now, this we have already done, if you remember, while extracting the RMS value of the sine wave. Remember that? Yeah. So this time it is not a sine wave, but a square wave. So we shifted it by 1.5 volts. You can see this arrow. It was 0 here, and to that we added 1.5, and therefore the part which used to be minus 1 has become plus 0.5, correct? And part which was 1 volt plus has become 2.5 volts. So Vs is equal to V3 plus 1.5. What is Vs? This is Vs. how much it is? V3 plus 1.5. What is V3? This is the V3. So V3 you are adding 1.5. So Vs is equal to V3 plus 1.5. I'm sure you understood this part. That is the hardware part of it. Now take a look at the sheet, Excel sheet. Here we use the term K. K is what is? Milliseconds. The interval between two samples is expressed in milliseconds. So 0 millisecond, 1 millisecond, 2 millisecond, and so on, going up to 19 milliseconds. And in this case, V3 happens to be 1 here, right up to this sample, it is 1. So it is 1 up to this sample. So 8 samples are 1. Then 8 samples are 0.05, just 0.5. And then 2 samples will be 2.5 volts. So 2.5 starts from here. There are 8 samples. Then there are 10 samples at 0.05, 0.5, and then there are 2 samples of 2.5. As you can see, it is 1.000 and goes up to this, up to 7, that is 1. Then 8, 9, 10, 11, 12, up to 17, it is minus 1. I'm talking about this V3. See, it is V3. So V3 goes like this, and then at the end again 2 samples which are plus 1. And what do you get at Vs? At Vs you get V3 plus 1.5. Vs is equal to V3 plus 1.5. You get it here. Now, as you did in RMS value extraction or calculation, this information, this data is fed to ADC, and ADC will do this conversion. 2.5 becomes 3413, so it is 3.13 constantly up to this. Then 0.5 becomes 683, so it is 683 up to this. Once again, you had 2.5 and 2.5, so 3413. From this, we are subtracting 2047 because we have added plus 1.5. So plus 1.5 means 2047. So from these samples, you subtract 2047. Why to do all this? Because the AD converter is not willing to accept these negative values. So we have added something so that the voltage becomes positive all the time, then converted it using AD converter, and then the values that you got, you subtract from it 2047, which is the equivalent of 1.5 volts. So you get this, and from this you obtain the volts. So this is how we get the volts in our measuring device. In our case, this measuring device is nothing but a microcontroller. So this was in the hardware. This was also in the hardware. This was in your microcontroller. This also in your microcontroller. And this also in microcontroller. All this had to be done because this was not acceptable to microcontroller. So we had to do these steps. 1, 2, 3, and 4, converting this into this. And once you have this, then our real mathematical jugglery will start. Here you have cos coefficients and sine coefficient. You have seen in the previous page that these coefficients you do require. So you tabulate them. So you have 2 arrays, this in one array in your firmware and this also in your firmware. You need to create arrays. And on what does this array depend? This array depends upon this. Look at cos coefficient here. The array depends on which harmonic you want. Here it is +1. And the number of samples that you are going to take. So accordingly, you get this array. So this array is standard. You are not trying to obtain it from any procedure of software. This is standard. So you form 2 arrays for every harmonic and store that array in your memory. of the microcontroller. So you have these two arrays with you, and then you mult-C. Mult-C means, what is the next step you had done? You had mult-C means what? Volts into cosine coefficient. Volts into cosine coefficient, you get this. 1 into 1 is 1. 1 into 0.95 is 0.95. 1 into 0.81 is 0.81, and so on. Then minus 1 into 0.81 into minus 0.81 is plus 0.81. Minus 1.00 into minus 0.95 is plus 0.95. So you have mult-C. C stands for cosine, S stands for sine. So you are multiplying with the coefficients. What you are multiplying? The signal. You are multiplying the signal sample with cos coefficient and storing it in mult-C. You are multiplying signal sample by sine coefficient and storing it here in mult-S. So like this, you complete right up to this point. Here what you do? Here you add up all these, and the value to sigma means you are adding, and the result of addition is 9.04. Similarly, you add all these 20 samples, and their sum is 9.04. This is sigma. Their sum is this. Then you square this quantity 9.04, you get 81.73. Similarly, this 9.04, you are getting this value on squaring. Then you add this and this. This comes to 163.46. Then you take square root of this. Square root of what? Square root of 163.46 and divide it by 10. This is the fundamental component value extracted from a square wave, right? So we are going to take this subject forward, and in the process I will not show 1, 2, 3, 4, 5 these columns. I will not show many of these columns, because eventually you will get this in the microcontroller. This is being obtained in the microcontroller programming, right? And this you already have in your microcontroller as 2 arrays per harmonic. If you are going to extract 5 harmonics, then you have 5 arrays. Then this is the operation you perform in software. So this operation you have performed in software, this also, this also. This was the array, not an operation, and then this was an operation, and this was an operation. Then the next operation was this and this. Further option was this, and final operation was has given you this information, right? So what I will do in the next tables, I will not show this. I will only start with this. This, of course, I will have to retain, and then I will do all this. Okay. So that is what I have done. I have to show the time markers, that is 1 millisecond. Then volts, how you get volts, that you have seen. You have seen here how you get volts. So I am not showing this whole thing again. This part I am not showing again. But it is understood, without this part you cannot arrive at this, right? So I come here. Here, what we have done just now, it is again shown in a small compact form. So cosine coefficients are, cos coefficient is cos 18 into 1 into k into 3.1416. 3.1416 stands for pi, and this is 180 degrees. Similarly, the sine coefficients. Don't make any mistake here. And mult-C is volts into cos. Just now we have seen volts into cos coefficient is mult-C, and mult-S is volts into sine coefficient. Same volts into sine coefficients is mult-S. This is what you get, and this we have just now seen in a bigger graph, in a bigger chart, that you get 1.28 here. Now let us go to the next slide. So in this side, oh, I have repeated the slide. Let us take this slide. Now we are taking second harmonic of the square wave. And we know that if there is a repetitive waveform, symmetrical repetitive waveform, its even harmonics are all 0. It will only have odd harmonics, first, third, fifth, seventh, ninth, and so on. So this will not have second harmonic, but let us verify. So once again we get volts as before. Then we perform mult C and mult S and arrive at this. When we perform this summation, that sum comes out to be 0. You will be wondering why you have so many numbers and why it adds up to 0, because it cannot have a second harmonic. This kind of waveform, which is symmetrical, repetitive, and fixed frequency. Now, similarly, this mult S also is 0, and therefore whatever operation you perform, you are going to end up with a 0. So our answer is second harmonic in this case is 0, which is what we expected. What we have done, we have maintained the hardware that we had done to start with. Let us go to next. Next is third harmonic. Now it should be non-zero. So we perform the same thing again, volts and multiplied by cos coefficient. So mult C, similarly got mult S. And we go right up to the end, up to this. Then perform the summation here and here. Then square these values. Then add this and this value. You get this. Take square root and divide by 10. You get this 0.44. If you remember, the first value was 1.24, which was the fundamental component. This is the third component. You can try fifth, seventh, etc. also. Then you will see that as you go for higher harmonics, the value keeps decreasing. From 1.28, it has come to 0.44. If you go to fifth, it will become further less. So it goes on diminishing. So now we take a different kind of waveform. This waveform is not a symmetrical waveform. So across this midpoint, it is not same. So in case of sine wave, it used to be same from over the entire cycle. You got showing like this. And this is very much unsymmetrical waveform. Now, this waveform will have odd harmonics also. We have tried to find out, and we have only changed the waveform, but we have not changed the circuit. That the hardware we have not changed. Hardware remains same, but instead of a square wave, this time to this hardware we are applying a triangular wave. This. It's a sawtooth wave. And the result is first harmonic, that is fundamental component, is 0.64. Procedure is exactly same. So long as we don't change the harmonic, this does not change. Okay. Now this has got harmonic, second harmonic. It will also have second harmonic. So this kind of waveforms have fundamental, first, second, third, all the harmonics. First you have seen. Have a look at the second harmonic. Procedure is same, and you get 0.32. Then we go to the last one. Here procedure is same, and you get 0.22, and you are calculating third harmonic. So friends, I want you to go back to this sheet, try to fully understand this procedure, this how to get coefficients for different harmonic components. You have different coefficients. Why? Because here you can see you have written first coefficient as this, where k is equal to 0 we start with, then it is 1 means first harmonic or fundamental. If you change this 1 to 2, then your coefficients will change. If you make it 1 instead of 1, if you make it 2, then the coefficients will change. So it will, right now it is 18 into 1, multiplied by all, 18 into 1. But if you go for second harmonics, it will start with 36, 72, and so on. Right now it is 18, 36, 54, and so on, right? So these coefficients depend exclusively on the harmonic you are trying to extract. Of course, it also depends on how many samples you take. So for one setup of hardware, you can easily change this, and you can have a multiple pairs of arrays in which you store these values. Okay, so I hope you have fully understood how to extract the harmonic components, and you also seen that some kind of waveform has only even harmonics, no, only odd harmonics, and there are types of waveforms that don't have even harmonics at all. So in this case, you did not have even harmonics, you only had odd harmonics. In the triangular wave, we had even as well as odd harmonics. So today I stop at this point, and we'll meet again. So see you in the next episode. Thank you.